Hello students, in this video we are studying that modes of failure or stability requirements of a gravity dam. In which manner the gravity dam should be failed or in future or for avoiding this failure, which parameters we have to take into consideration. In this video we are going to study. After studying all the forces, we come to know that which are the resisting, which are the external forces, or which are the exerting forces, or which force should be taken into consideration in the first stage. So let's start. The modes of failure, that is, the following are the modes of the failure. The manner in which the gravity dam should be failed in a future or in a very short period without giving us a warning. So the overturning, sliding, compression or crushing, and the tension. In this manner the gravity dam will be failed. So let's start with our first mode of failure, that is overturning. See, overturning of a dam takes place when the resultant force at any section cuts the base of the dam downstream of the toe. In that case, the resultant movement at the toe becomes clockwise, or on the other hand, if the resultant cuts the base within the body of the dam, there will be no overturning. See, when the resultant force, what is exactly resultant force? After calculating all the forces, we have to divide, or we have to uh, properly mention that which are the horizontal forces, which are the vertical forces. So after calculating all these forces, after calculating the moments which develop because of these forces with respect to their CG, or with respect to their distance from the toe part. So after analyzing all this part, we have to calculate the resultant force, the average, the total force which are acting on the gravity dam. So if this resultant force section cuts the base of the dam downstream of the door, or to towards or afterwards of the toe section, then this dam will be failed in a overturning section. Or if the resultant cuts in the within the body of the dam, then there will be no overturning. Okay, so for the stability requirements, the dam must be safe against the overturning. Okay, means what? If for example, if one person is standing, so if there see if he is standing towards the face of the east, and from the west part some force are exert, or some force is coming and exerts him to push towards the east section. Okay, so if we cannot control him, or if he himself cannot control to move further towards the east, so what happened, he falls down, or he falls down on his face side, and he overturns. He fails down on the faced side or on the mouth side. So if he want to resist that forces, what happened, he push back his balance and push back his force towards the west section. So what happened, the forces which are exerting on him, or the resisting force, or it's his own weight will resist that force. So the it happens because of what? See, we have a foot, we have a hill part, we have a toe part. Here also the gravity dam will be analyzed along with respect to the hill and toe part. So hill means what? Our the feet point, or the last point, the foot parts, the flat surface, this is a hill. And toe means what? The finger side points. So if I gave my all pressure, the all my weight on the toe portion, and if the portion and the forces if coming back towards the waist, and I want to resist that. So what happened, what I am doing this, I just breaks my toe, or I just gave my resist force on the toe portion, so that it gave me the strength to react against that exerting force. So similarly here also, gravity dams, if there is no other resisting forces to exert to act against that exerting forces, so the dam definitely fell in a overturning section. So if we want to keep the dam in a safe condition against the overturning, we have to find out the factor of safety against the overturning, which can be find out by using this formula, that is factor of safety is equal to the summation of writing movements. Writing means the positive movements, the movements which is comes, or which can be treated as a positive one. This is known as a writing movements, and divided by the summation of a overturning movements, that is a negative movements. So the ratio will give us the factor of safety against the overturning. So since the magnitude and the direction of each and every force considered in the previous articles are known, so we know that the direction of the if we want to find out the water pressure, so we know that the water pressure always acts in a horizontal, so this is considered as a horizontal pressure. Self weight, it is considered as a vertical pressure. So we know that the direction and the magnitude of each and every force. So we also know the moments about the toe. We can easily find out all these magnitudes according to the forces, or with respect to the center of gravity of these forces. So this factor of safety then should be calculated, and this factor of safety against the overturning should be less than 1.5. If the value is greater than 1.5, then definitely this gravity dam will be fail in a overturning manner. So in this manner, or in this process, we can find out, and we can protect our gravity dam against the overturning. So next is the sliding. Now we saw one example that how the overturning will be avoided. Now sliding means what? A dam will fail in sliding at its base or at any other level if the horizontal forces causing sliding are more than the resistance available to it at that level. If the horizontal pressure means the water pressure is maximum, is greater than its resisting weight, then at any level, or at this level, this dam will be fail in a sliding manner. So the resistance against the sliding may be due to the friction alone, or due to the friction and shear strength of the joint. So this happen because of the friction or shear friction. The shear strength develops at the base if benched foundations are provided, and at other joints if the joints are carefully laid so that a good bond develops. The shear strength also comes into play because of the interlocking of a stone in a masonry dam, obviously. So because of these reasons, the shear strength will be developed in the gravity dam, and because of this shear strength and because of the friction, this sliding will be occur in a gravity dam. So shear strength also comes if this shear strength is not taken into account, the factor of safety is known as, and we have to find out the factor of safety against the sliding. So this is defined as the ratio of actual coefficient of static friction, that is a mu, on the horizontal joint to the sliding friction. So this ratio gives us the factor of safety against the sliding. This sliding factor is the minimum coefficient of friction required to prevent the sliding. If the summation of the horizontal forces causing the sliding, and if the summation of B is the net vertical forces, then the sliding factor will be find out according to the, or with respect to the theta, it is equal to the shear, or yes, we can say that the sliding factor, it is equal to the tan theta is equal to summation of horizontal force divided by summation of vertical force. And factor of safety can be find out against sliding, it is equal to the mu, that is a coefficient of static friction. The value of mu varies from 0.65 to 0.75. It multiply by summation of vertical force divided by summation of horizontal force. And this value, the factor of safety against the sliding, should be greater than the value which are shown in the table, which is given by the IS code of 65121972. This IS code gave us some values that if the it is considered that, see, the table is again coming in the next slide, but before this, if we say that this sliding will occur because of the friction, and this is because of the shear strength also. So when the low gravity dam is considered, so the low gravity dam should be safe against the sliding considering the friction only. However, in a large dam, the shear strength of a joint should also be considered for an economical design. So, if the gravity dam is a low one, or low gravity dam is considered and is to be constructed, then the only the friction factor is considered. But if the gravity dam is considered to be a large, or considered to be a high, so here because of this high or large length and the longer length, we have to provide the various joints also. So because of this joint, the shear strength will be developed, and we have to consider this. So the factor of safety in that case is commonly known as a shear friction factor. If we consider, or we have to find out the friction factor of safety just because of the friction, this is calculated by using a simple formula, that is mu multiply by summation of vertical forces divided by summation of horizontal forces. The mu value, which is varies from 0.65 to 0.75. The value when the shear strength of a joint will be considered, then we have to find out the factor of safety, or we can say that the shear friction factor. So it is calculated by the given formula, that is mu, again mu, into summation of vertical forces plus a. A is nothing but area of a joint. The joint will be, that is given, the area of joint, that is B, width into 1. We are designing, or we are calculating all the forces with respect to the unit length of a dam. So according here also, the unit length of a dam will be considered. So for finding out the area of a joint which is placed in the in according to the length of a dam, so width into a 1, that is unit length of a dam. So A is the area of a joint. C is nothing but the average cohesion or shear strength of a joint value. So the value is also given here based on the material. So if there is a generally the value will be taken from 1300, that is 1300 kilonewton per meter square to 4500 kilonewton per meter square. It is applicable, and it is adopted when the material is a good rock, and when we are using the concrete, or then the shear strength of the joint value is ranges from 650 to 1300 kilonewton per meter square. So simply the gravity dam is constructed in concrete or with the help of a concrete. So ultimately we are adopting value of C as a 652, in the range of a 650 to 1300 kilonewton per meter square, divided by summation of horizontal forces. So by using this formula, we can find out the shear friction factor when we are considering the shear strength of a joint in the larger gravity dam. So we have to calculate the shear friction factor also. So here the table is given. Yes, this the table. So according to the loading condition, or based on the IS code 65121972, here are the value of a factor of safety against the sliding or a shear friction factor also. See, loading means what? Just I want to give some just introduction and some information about this loading condition. See, we have a two recommendation, that is USBR and IS recommendation. So according to this recommendation, we have the loading condition also. So what is exactly that loading condition? See, we have according to the normal USBR condition, we have a normal load condition. In that, we have a normal water surface elevation, ice pressure, silt pressure, and normal uplift. Then in the uh, in that normal load combination, again, if the flood situation occur, then maximum water surface elevation, that part also we have to consider. Even we have to consider the earthquake force also according to the USPR. I'm telling you. Then we have an extreme load condition. In that, the flood water elevation, silt pressure, and extreme uplift, which uh, don't have a drain in operation to pass away this uplift pressure and to pass away this seepage water. This is considered as an extreme load condition. And the reservoir empty condition means there is no water on the upstream side, so only the self weight of a dam will be considered and will be calculated. Again, according to the Indian standard recommendation, which is based on the IS code 6512-1972, see here they gave us a condition based, they gave the name alphabetical order, that is A B C D E F G. Okay, so using the safety factors and the details, the components which are considered in that particular loading that they are given us. See, the first basic condition is A condition, loading condition A. Here, simply the dam, just dam is completed, but there is no water in the reservoir. Reservoir is in an empty condition only. So though if the water is not in the upstream side, so obviously the tailwater is not generated, means only dam is there, or the sulfate of a dam is considered. This is the loading condition A according to the Indian standard. Loading condition B, in that the water is there, water is stored in the upstream side, so full reservoir elevation. Then because of this water which is stored on the upstream side, we have a tailwater on the downstream side. So the water pressure on the upstream side, tailwater on the downstream side. Then see, the water pressure is there on the upstream side, so through the cracks, through the pores, the water will get percolated into the base of the dam or in the foundation of the dam, and this part of a water will exert the pressure on the water. This is considered, this is called as a uplift pressure. So the water is there, so ultimately the uplift pressure will arises. So water pressure on the upstream side, tail pressure on the downstream side, uplift pressure. Then if silt is there, if the particle of the silt is carrying out with the flow of the, so we have to consider the silt. And if this dam is constructed in the colder area, so we have to consider the ice pressure also. So this is the loading condition B, normal condition. We have only these forces only. Then the C condition means the maximum flood condition. We have a maximum flood elevation, means we have a water level which is higher than its normal level. So the maximum flood level or water level, then the tailwater because of the flood, then normal uplift and silt. Then the load condition D, when there is no water in the dam, but earthquake pressure will be applicable. So this is the condition D. Load condition E means what? The load condition B means the normal condition plus earthquake. So this is a normal condition E. Load condition F means what? The maximum flood level will arises and with the extreme uplift pressure, means there is a no chance to discharge the uplift, no chance to discharge the seepage water. The seepage water accumulated inside the body of the dam only. So it does not get any outlet to pass away on the downstream side. So because of this, the extreme uplift pressure will arises in the body of the dam. So this condition will be treated in the loading condition of a F. And loading condition G means what? The normal condition, that means a normal water pressure, normal water level is there, tailwater is there, uplift pressure normal is there, silt pressure is there, and along with this again the uplift pressure is not a normal one because the drainage gallery is not working. So again the water, seepage water will be accumulated inside the body of the dam, and this exerts the major force on the body of the dam. So these are the conditions. So according to this condition, the factor of safety against the sliding, against the shear friction, they are given here. So for the ABC condition, the factor of safety against the sliding is 2. Generally the factor of safety should not be greater than the 2. Then the shear friction factor will be 4. Then for the loading condition D and E, the factor of safety against the sliding is 1.5. See, you can see the shear friction factor will get doubled. Okay, only in the F and G condition you can see the 1.2 is the factor of safety against the sliding. So here the shear friction factor will be a 1.5. So in that manner we can find out the shear friction factor. See, factor of safety means what? We have to give a permissible limit and permissible value. If the value exceeds beyond this value or beyond this limit, so we can easily say that this structure will get failed soon or in upcoming days, so without giving any warning. So we have to consider this. So we have to taken into consideration that this factor of safety is very important role in overturning also and in sliding manner also. The compression, the gravity dam will be failed, or the mode of failure will be in a compression or crushing zone also. So what is exactly this is? See, in order to calculate this normal stress distribution at the base or at any section, we have to know the total horizontal force and we have to know the total vertical force. So by calculating this only, we can easily find out the resultant force, that is capital R, which acts at the any point on the base of the structure or based on the dam. It is denoted by a small e, or it is called as a eccentricity. If you study the structure part, so on the columns also, on the center, if the load is acting on the column, so the point from the or from the center of the column, center section of the column, the point on which the load is acting, this point is nothing but the distance from the center of action to the application of this load point is known as a eccentricity. Here also the resultant which is acts on the base of the dam, and from the center of the dam to the point where the resultant acts, it is nothing but a eccentricity. So this normal stresses at any point on the base will be the sum of direct stress and the bending stress. So direct stress will be calculated by V, that is vertical forces divided by the area, that is V into 1. 1 is the unit length of a dam, and bending stress will be found out by the moment multiplied by Y divided by inertia forces. So according to this section, we can find out the bending stresses, and the total normal stress is given by the vertical forces divided by the width into bracket 1 plus or minus 6 into eccentricity divided by the B width. See, this summation and the addition of this direct stress and bending stress will give us a total normal stresses, which acts on the toe and which acts on a hill also. The positive sign will be used for calculating. See here you can see that the plus and minus both signs will be used. So positive sign will be used for calculating these normal stresses at the toe, and the because the bending stress will be compressive there where at the toe section, and the negative sign will be used for calculating normal stresses at the hill, because the bending stresses is very, or we can say that it is a tensile one at the hill section. So for the toe section, the formula will be used as normal stress at the toe, it is equal to the vertical stress divided by vertical forces divided by the P width into 1 plus 6 into eccentricity divided by the width, and the normal stresses at the hill will be calculated capital V upon B width of a dam into bracket 1 minus 6E upon P. So generally by using this formula we can find out the compression or the crushing, or the we can say that the normal stress which occurs on the gravity dam. See according to the diagram, I will show that diagram in the next slide. See, according to the diagram, the normal stress distribution for a general case when the pressure at the both toe and hill are compressive. The maximum compressive stress occurs at the toe, and for the safety, this should not be greater than the allowable compressive stresses for the foundation material. Hence, from strength point of view, this normal stress should be less than or equal to the allowable compressive stresses, that is F, or the value will be 3000 kilonewton per meter square. Foundation material is made by a concrete only, so the compression or compressive stress, it is equal to the 3000, so the value should be less than or equal to the 3000 kilonewton per meter square. It should not be exceeds than that value, and the eccentricity is equal to the B by 6. We get the normal stress at the toe is equal to the 2 or twice vertical forces divided by the B. So the corresponding stress at the hill in that circumstances will evidently be 0. So these are the condition, this is the method for finding out the compression pressure or the normal pressure on the gravity dam. Now the tension. We know that the gravity dam is constructed with the help of a concrete. Concrete has the characteristic to compress. It is good in a compression zone. Now what exactly affects and which factors affects on the gravity dam to follow the tension or tension failure? See, according to the normal stress at the hill, see, according to the normal stress on the at the hill, we know that the equation is vertical forces divided by the width into bracket 1 minus 6 into eccentricity divided by the P width. So it is evident that if E is greater than B by 6, if the eccentricity is greater than B by 6, see it is a condition. If the eccentricity it is equal to the B by 6, then we can say that yes, the gravity dam is safe against or in the compression zone only. If it is greater than the b by 6, then the normal stress at the hill will be a negative, or it is tensile one. Okay, so no tension will should be permitted at any point of the dam under any circumstances for moderately high dams. For no tension to develop, the eccentricity should be less than b by 6. It is the condition when we are saying that the dam is safe in the tension zone, then we have to uh, keep this eccentricity should be less than p by 6. Means what? The resultant should always lie within the middle third of the gravity dam. See, in case of extra high dam, that is 230 to 260-meter height of a dam, small tension within the permissible limit is generally permitted for the comparatively small periods of a loading, such as a heavy flood or earthquake. See, in the higher dam and in the higher height of a dam, generally this some limit of a tension will be permitted. So, or it is because of the heavy flood and the earthquake only. So this is the actually the tension will occur on the gravity dam. See what exactly happened, what the effect of this tension, what exactly it gives us. Since the concrete cannot resist the tension, we know that the concrete has a characteristics in the compression only. A crack develops at the hill, which modifies the uplift pressure diagram. Yes, because of this tension, the uplift pressure diagram will be modified according to the uh, or based on the crack formation. So, due to the tension crack, the uplift pressure increases in magnitude and net downward vertical force or stabilizing force reduces. The resulting force thereby gets further shifted towards the toe. See, basically, we have to keep this resultant force within the body of the dam in the point of a factor, in the point of a safety purpose. So, because of this tension, this resultant force shifted towards the toe, and this leads to further lengthening of a crack. The crack will be lengthened more and more. The base width thus goes on decreasing and reducing, and the compressive stresses on the toe goes on increasing till the toe fails in a compression. Means what? Tension cracks and the tension force is uh, what do we say that is this tension tracks gives the or it increases the compression stresses on the toe side, and ultimately the gravity dam fails in a compression zone. So we cannot say that the gravity dam fails in a tension. It is responsible to develop the compression stresses in the gravity dam, and the gravity dam will fail in a compression zone only. So this is how the gravity dam will fail. So to resist and to avoid all these failures, we have to find out the factor of safety. After calculation of the forces, then we have to calculate the factor of safety against all these points, and we have to gone through all this. We have to gone through the gravity dam through all these force and all these processes. So I hope you understand this mode of failure or stability conditions of a gravity dam. Thanks for watching this video.